I appreciate everyone coming in and attending. The intent of this is to really take a look at the changes and the improvements that have been made within the lithium supply chain with respect to new lithium reserves. I'm going to say unconventional reserves that are now being pursued, and in part why those unconventional resourcing pursuit is because of DLE or direct lithium extraction technology advancements, as well as others. So I just wanted to touch on that, kind of a high view, and then we'll drill into, there we are, and then we'll drill into the specifics of it. So the topics I wanted to cover today was global lithium demand, just really set the tone of kind of where we are within this with respect to the supply chain on a global aspect, the challenges in the supply chain. Demands have grown significantly. Can we, at this point, we're outpacing where our productions are, and maybe even where I'm going to say our resources are, but that's a fallacy. Unconventional lithium sources, take a look at that. Direct lithium extraction, what is that exactly? Optimizing from that DLE. How can we optimize the performance of it? And part of that is forward osmosis, or FO. How is that applied within the DLE flow sheet? And lastly, optimizing the FO configurations and configurations. So without ado, so on the global, on lithium supply right now, just to get a foundation of it, is what we're talking about 85% of the lithium right now being produced is going towards batteries, specifically for EVs or electric vehicles. If you take a look at it, just on the left-hand side, that's an 18650, 18 millimeter by 650 millimeter small battery, looks like a AAA. And inside of that is about 0.6 grams of lithium. The lithium is actually is absorbed into or incorporated into the cathode. But when you take a look at the sheer size and the weight of it, there's not a lot of lithium in there. However, when you take a look at an electric vehicle that takes up to, on average, let's say about 7,000 lithium ion cells, it starts to add up quickly. So one EV vehicle would require about 4.2 kilograms of lithium. And when you start taking a look at how many of those EV vehicles are going to be produced and put into the environment over to 2030, you can start to understand that there is a huge jump within the supply and demand curve. So we take a look at present day, just to kind of give everyone a flavor of it. From 2010 to 2021, there has been a steady increase. And I said 85% of the lithium is used in batteries. Lithium is used in other aspects of ceramics, lithium greases, and so on. But 85% is going towards the EV market. And when we take a look at that, 2021, from USG and different stats, right now our production of lithium is about 100,000 metric tons. So sounds like a lot. Where is that lithium production coming from? If we were to break that out into a global basis, is that the majority of it's coming from Australia, which is hard rock. So spodumene and pegamites and so on. Then Chile, China, and so down. Now, if we take a look at, Chile, Argentina, and Bolivia, really about a third of the lithium is coming from that location. So you take a look at it, that we're at 100,000 metric tons produced annually, and really it's distributed across about 3 regions. So not a lot of diversity, which is a concern when you start taking a look at the geopolitical aspect of it, is that if there was an upset with one particular country, and your country doesn't have access to that lithium, then there could be a huge upset to that. Via why there's been a huge push and initiatives through several countries, through the US, through the UK, to develop their own resources. because they don't want to be held ransom by other countries. So, and plus just the EV market, which is great as sustainable, that is just going gangbusters with respect to the displacement of conventional combustion engines. So when we take a look at, the 2030 forecast, where we are, the projections to 2030, I know that's a little bit out. Maybe most won't be around. Hopefully I will. But when we take a look at that, our current production is 100,000, and we're forecasting 2030, 2.1 million metric tons. So a 200,000% growth and a production difference of around, let's round it off to 2 million metric tons. I'm sorry about that. I was just informed that, sorry for 1 second here, that there are people waiting in the lobby. Sorry. Oops. Sorry about that. There. And we'll start back up. Again, I apologize. So there is a significant difference between where we are and where we want to be. So the question becomes, with that much of a gap, is that ocean crossable? And let's take a look at, to answer that, really, let's take a look at our current supplies of lithium globally. So you may be familiar hard rock, which is pegmite, kind of magma, spodumene is probably the most common. So you're doing open pit mines, quarrying, and crushing that stone in order to extract the lithium content from it. It's very energy intensive. It uses a lot of water, and there are byproducts to that. You need to cook or roast the spodumene to kind of release the lithium, and you have to acid wash or acid wash with that in order to extract the lithium from it. So there are byproducts to it, and it's just energy intensive and so on. But that accounts for right now about 50% of the production globally. Clays, that I just added that in there. Back in Nevada, there's clay deposits and so on. There's another source there. Clays are relatively new entry into the lithium source, and by saying that there's a lot of development still required to figure out how to extract the lithium from those clays. So I put that there because it is a vast reserve that we could tap into, but we don't have the tools yet just to do it. So it's something to keep on your radar. And the last one is brine, which is a aqueous solution. And that accounts, as we indicated from the previous slides, probably about a third of our lithium production. I'm sorry, there's people still in the waiting in the lobby. I'm not too sure why that is occurring. I really apologize for this disarray. There we are. At the end of this, I'm going to say, don't use Teams. I apologize for you, and I appreciate your patience. There we are. So brine. So you're probably familiar with, these are beautiful in South America. Beautiful pictures. These aquamarine ponds, which span, hundreds, if not thousands, of acres. So take a massive amount of land, but the nicety of these, this has been in production for a long time, is that these are solar thermal. So you're pumping brine to the surface from a sublevel up, and you're filling these ponds, and you're allowing the solar thermal evaporation to occur. And as the water leaves, it starts crystallizing. So it is a unique approach. And solar ponds, you really need to have a high concentration in order to do that, which typically it's really allocated to specific regions, so it's not abundant. But the nicety of the brines is that it's liquid, so I can pump it. It's transportable. I can move it around. It's easy to manipulate, much easier than these aspects. And because of the high concentrations, it's actually one of the most profitable to do. The downside of these evaporations is that because you're relying on thermal evaporation, it takes a while for these for the ponds to evaporate and to allow the crystallization to occur. So when you first put an evaporation pond in, it could take up to 2 years before you can start production. And after it's in production, it may take a year as you pump in. So there's a long production cycle within these. And when you're talking about a demand from, going from 100,000 to 2.1 million, the timing also comes in is how quickly can you build these plants? So taking a look at the resources available to us, well, there's an abundance of lithium brines in the world located, and that can be from continental brines, which are basins, have very high concentration, typically located in South America. And because there's such a huge demand, and right now it's outstripping production, and the other component to it is that when you first do mining, you go for the high purity and I'm going to say the easy minerals sitting on the ground, easy to access, high purity, not a lot of contaminants, but those premier reserves have been used up. So now what we're challenged with is moving forward and looking for unconventional reserves. And part of those unconventional reserves are moving towards to geothermal brines or oil-filled brines. It's less concentration, as I said, indicated, and these are just round numbers. There's variations because these are the geological aspects is that when the water touches something, it absorbs it. So the region, the depth and so on changes. So there's a lot of variability in these, but as a typical range, you would see that geothermal lithium is 300 to 2000 ppm, but I'd say that it's really more so on the lower end of let's say 300. You can even be 100 to 300. And then you get into the oil fields, which is lots and lots of oil fields, and that could be even extracting lithium from produced or flowback water from bringing a well in, or could be an old well. But those wells can be used as a source of lithium. They're lower in concentration, but there's enough of them that on a per capita is that it would make up for that 2.1 million deficit in production. So there you have on the lithium brines is that one is that we have to make up the deficit of 2.1 million tons of lithium over a current of 100,000. We have to find new reserves or resources. And the challenge is that, well, we're going to have to push into unconventional areas or reserves in order to meet that production. One is that there's enough lithium in the world. I'll give you an example, is that the ocean has an abundance amount of lithium. The challenge is that the concentration is so low, it's not economically viable in which to extract it. So the challenge is to go out and find new reserves that have lithium contents that allow economic viability in their production. And brine is a perfect example of that. So in taking a look at the DLE, I mean, what do we mean by direct lithium extraction? Well, the first thing is that, from talking to engineers and clients is that sometimes they get the stigma that it's some type of technology. It's not a technology. It is a type of process. So it's not specific to a technology. And as we go through this presentation, you'll see there is a lot of variations with respect to DLE. Currently, I'm engaged probably in about 35 different lithium projects or DLE, and they all have variations to them. So there is no real standard approach. and we'll get into the reasons for why for that. But you can take a look at the flow sheet. Typically, what you're seeing here is, well, here's your brine aquifer. This has the lithium, but also has, remember, it also has other contaminants in there, things that we don't want, calcium, magnesium. We pump that up, we put it into our reactor, and essentially think of it as it's a loading tank where we have, our absorbents or ion exchange, in which the material will directly reach out into the bulk and pull those ions into their into either the absorbent or into the ion exchange or resin, I should say. And when that's complete, when it's soaked long enough and it's absorbed long enough, and typically you're taking a look at the efficiency of probably about 95% extraction of lithium from those brines. Once it's been the resins or the absorbent's been loaded up, then it is the resins are then loaded into another tank. It's washed. Basically, it could be a chemistry, or it could be just a water in which to elute the lithium off of the materials, and then from that produces our lithium concentrate. And from there, we pass it off. Really, from there, it turns into a conventional process. So now you could be taking the lithium chloride, and then you're going to convert that either to lithium hydroxide or lithium carbonate, depending on what the end product is. So this is the uniqueness of the process. So, the type of the DLE technology used, when you take a look at, well, why you've got, as I said, I'm tracking about 35 different, or engaged with 35 different lithium flow sheets, and there's variations to it. Well, why is that? Well, the DLE technology has to be tuned to the actual lithium brine feed. As he said, is that different geologies will impede or impart, I should say, different characteristics, different contaminants, different lithium concentrations, different qualities within the brine. And the DLE process needs to be attuned to that. So again, the DLE technology is tuned to what the lithium characteristics are, and via the reason why there's a lot of variations to the DLE technologies, because you're looking to optimize that process. So when I said the absorption, I mean the direct lithium extraction, well, what is that direct part? Well, there's two typical materials that is used. I should say there is solvent extraction, but I didn't touch on that. My personal opinion, I'm not a big fan because it has, the chemistries used are sometimes very toxic and very violent to the industry. So for this presentation, I'm just going to focus on ion exchange and absorption materials. Ion exchange resin, if you have a softener at home, then you're very familiar with this, is that you have a sort of like a polymeric bead that has a functional group on it. And what that functional group is set up is that it has a specific affinity for lithium and no other contaminant. So when you put that resin in, you can either flow it in or have a column, like you can see down below here, is that it's going to absorb, or I should say, reach out and extract the lithium. And in this particular case, the resin is going to pull it into the functional group and release something that it doesn't want. It could be sodium or something, some other ion that's been regenerated with. So that's the one aspect, is that you can have the ion exchange. Very efficient. Lots of people are using that. The other one, and apologies, this is an electron microscope view of it, is getting right in, is the absorption material. A little bit different than the ion exchange, but the absorption material is specifically absorbing lithium onto its surface and holding it there, and no other contaminants. So two basic functions, which are, I'm going to say, probably compromise, my own opinion, probably about 90% of the DLE technologies out there. Take a look at the difference of the materials used, and there's uniqueness within these, the ion exchange resin or the absorption materials. There are some companies that have specific proprietary recipes and hold their DLE technologies very tight to their chest. There's others that, such as Dow or DuPont, have resins that they sell readily to the market. So these are the different, could be alumina-based, could be magnesium, titanium. There's other materials out there, but I just wanted to kind of give you an understanding of the variations of the extraction, either absorption or ion exchange. So taking a look at the, when I said there's variations to the DLE process, and there's lots globally. And again, it is your DLE process is going to be tuned to what your the characterization is of the brine. Again, contaminants, lithium concentration, temperature, and so on. So I've just put together a couple of examples just to kind of give you a flavor. So when I say variations to this, one is E3 Metals. This is their process. What they're doing is they're using, oil wells to extract low concentration, but they tune their system is that even at a low concentration, they can extract the lithium directly from it. Emerit. This one is this particular application is down in South America in the salars, and you can see there's their absorption material. This is a different flow process or flow sheet in contrast to the previous one. They're using membranes, they're using reverse osmosis, and then they're using a thermal evaporator in which to concentrate. They are extracting the lithium, and then they are purifying it and concentrating even further through this particular process. The last part of this, as I said, when you get to this point, is that you go through conventional chemistries to basically polish and convert the material over to what you're typically looking for. Typically lithium hydroxide or lithium carbonate. Emerit, there's another application. I just pulled this up. So the previous one was on a salar in South America, which is very high concentrate. And this one is actually in Europe, and it is a geothermal lithium brine. So they have found reserves down below through the different geology, and they'll be able to pump up that brine. And it has because it's a deep and geothermal, there's actually an energy content to this as well. So not only does it contain, a valuable mineral, lithium, it also contains a value of energy. And this particular aspect is that they can use that geothermal energy to actually generate power in order to run their processes, or they can create that heat content, create a district heating. So they will sell that heat to local communities, which then eliminates or displaces natural gas and oil. So very much of a green approach to and sustainable to the DLE processes. So again, just giving you a variations of what the differences are in the flow sheets and the pros to them. Standard lithium, this is another technology. This is absorption materials, where they are taking, in this particular one, it is it's a bromine reserve in which they are, pumping that through. It goes through a loading tank. Lithium gets loaded into it, then goes to a washing tank to get rid of some of the additional contaminants, and then finally it moves over to the conventional chemistry where that lithium is then converted. In this particular one, they're converting it to lithium carbonate. So nicety of these systems on the brines, you notice that a lot of them you're pumping up from the aquifer or the brine source, and then you're pumping back down. So the sustainability to this is that I'm just taking what I want and then I'm putting everything back. So it is a very straightforward, I'm going to say environmentally friendly in most cases of this. I think it's important to take a look at is that down in South America, one of the challenges there is that they're pumping from the brine aquifers, the shallow aquifers, and they're just pumping that water and pumping it onto the surface. You can set up in hydraulic imbalances, and that's one of the I'm going to say the challenges or topics of conversation in South America, is that as you pump down those brine aquifers, well, then you get kind of a low pressure zone, and then you can start pulling fresh water into them, which can be a challenge. So to me, is that if you can always do a hydraulic balance, that's the way to run your DLE process. And I think the last one is another geothermal, and this is in the UK. Again, you're taking a look at areas when from the very first slide when we said, okay, you know, it's 100,000 metric tons. We have a deficit of 2.1 million, and then the other we talked about the geopolitical aspect of the supply chain of being able to get access to the lithium. So you're seeing a lot of I shouldn't say companies, countries that have never mined lithium before are now being able to, with the DLE technology, are enabled to start mining and producing their lithium where they've never produced lithium before. And UK is a perfect example of that. Whereas all the lithium was bought offshore, a different company, but now with the DLE technologies, it's enabled them to go after, again, these unconventional reserves. And with the DLE, the advancements in that technology is to economically and viably produce this lithium. And again, this is just pumping up the geothermal brines, extracting, and then pumping that back down. One of the beneficial use, again, is heat to run that process. So getting back to, again, why the DLEs, there's so many variations to it, is that the DLE technologies are, again, tuned into the characterizations of the brines. So in order to optimize your DLE process, it has to be synergistic and complementary to that feed source. Straightforward. So the challenge is that, well, what happens if there's, you know, something happens to the brine source? There's a variation to it. You know, as you're pumping these down, maybe the lithium content goes down, maybe some contaminants come up. You know, is the DLE technology robust enough to compensate? Well, there is a, you know, there is variations that they can do, but you couldn't switch to a brand new lithium source. You would have to retune that process. So in looking at the challenges of the DLE market, the approach that we took is that, well, rather than tuning the DLE process to the source, well, why don't we just tune the source to the DLE process requirements? And this is what the next aspect of the presentation is about, is that, well, how do you tune the feed source to complement the DLE processes? So to start is we use forward osmosis. Forward osmosis is a membrane technology. It is unlike, I'm going to say it's the opposite to RO. But just to make sure everyone is on the same page, I won't belabor this since a lot of you, I think, are quite knowledgeable. But the intent here is that if I was to take a U-tube and fill that with clean water, and this represents a semi-permeable membrane, allowing the net transfer of water molecules and nothing else. If I was to fill that with water and have that semi-permeable membrane, and I was to take salt and drop it into one side of that U-tube or solute, what you would find is that automatically and spontaneously the water would start migrating or being drawn across the membrane from a high water concentration to a low water concentration. And it will continue to do that, this delta H, until the pressure and gravity will prevent it from flowing. So a crude analogy is think of these solute molecules as magnets. Is that when you drop these solute molecules into the water, it starts pulling and attracting the water molecules across. So Definition of osmosis, won't belabor this, is that you're going from a high water concentration to a low water concentration spontaneously through the use of the chemical energy or osmosis imparted by the solute that you apply into the water. What type of solute? Well, it could be a salt, sodium chloride, sodium bicarbonate, but anything that really that you can put into the water to pull it across, could be even a salt molecule, can be used as a draw solution. So you're not limited to any specific chemistry or species. So taking a look at the differences, and I'm sure you're all familiar with RO, is that with RO is a pressure-driven device. And it's saying that that it is typically limited by the osmotic pressure. So RO is great when we do our modeling. We take a look at the chemistries and characterization, the Fouling indices and so on, and work it through. But we know that there's a physical limitation to the operations of an RO, and that's imparted is that when if the more and more solute or salts or TDS that I have in my water, the more pressure I'm going to have to apply to overcome that osmotic energy to push it through the membrane. So in this case, I'm going from a low concentration to a high concentration of water. And off to the right here, just as a rule of thumb or just as reference, you can say normal operations, a TDS around 35,000 ppm, which would typical of like salt seawater. Yeah, you're operating around 500, maybe 600 psi, maybe 700. But as you can see that as the TDS goes up, or the solute in the water, that the energy and the pumping energy required to overcome the osmotic energy goes up significantly. So I think that I'm aware that probably the highest pressure right now is around 1100, maybe 1200 psi. But when you get up that high, what happens is that you're now into an operating range of the RO, where the material constructions, it's high grade stainless steel. There's no plastic in this because you're talking over 1000 psi. So the construction, your capex cost goes up significantly, and your opex costs go up significantly. I look at RO as the gold standard. If you're operating at around 30,000 ppm 35, you can't touch an RO in performance. You're looking at maybe 2 kilowatt per cubic meter. It's great. But when you go above that operating range, it loses the efficiencies and the operating costs go up significantly. So this is where forward osmosis comes in, is that where an RO operates very efficiently on relatively low TDS, FO performs perfectly within high TDS. So in reference to that, I mean, we can go up to TDS streams up to 240,000 ppm. That's well above this 80. Now, in relationship, if I was to take a look at that, the osmotic energy which an RO imparts versus an RO, the energy required for pressure, the osmotic energy used to draw the water across, which is imparted onto the water, is equivalent, not pressure, but it's equivalent to the pressure of 3,200 psi. That's how much energy is reaching across that semi-permeable membrane and pulling the water molecules over. So an incredible amount of energy. So you would never be able to do that within an RO. So the other aspect to the operation of an FO is it allows us to operate in very challenging waste streams, which is very high TDS, high fouling propensity, high scaling propensity, things that are typically challenging to an RO system, and why it requires such an intensive pretreatment system. Could be a roughing filter, a UF, a softener. I mean, you have to have the pretreatment system in order to operate the RO.
If I could jump in,
but
I just want to connect the dot.
Moving forward, is that taking a look at, well, the differences between a pressurized system and an FO system is when you take a look at when the feed comes through, is that you're pressurizing and you're pushing the water, but also the bulk in any solids towards the active layer of the membrane. As you're aware, I mean, as we're permeating, we're developing a polarization concentration layer here, as well as solids, and I'm pressurizing that. So I'm compacting the solids into this, into the membrane. In some cases, severe is you're pushing the solids right into the active layer. And when that occurs, you've got irreversible flux loss. No amount of cleaning is going to be able to recover that loss area. So that is why with RO, a lot of cleaning regimes, from acetic acid to hydroxides and so on, is because you've developed this this layer and you've compacted it. Whereas in FO, you're not compressing; it's not pressure driven. Remember, the solute is reaching across and drawing the water across the membrane. In doing so, it's not pushing the bulk solution towards the membrane. It's just drawing the water across. So let me just emphasize at this point is that it doesn't mean that FO membranes don't foul. That's not the case. But it's the characterization or the matrix of the solids. It's loosely held onto the surface of the membrane, which then facilitates easy cleaning. So in a lot of cases, because the membranes are so loosely adhered to the membrane, is that we can just use the permeate water and just flush the membrane. And when we do that, we remove it, our foulants, and we get reversible flux. So we recover our flux, typically around 100, 99 to 100%. So in saying that that's the operations, the difference in the operations between RO and FO. The next is that, well, when would you use FO? Well, it always comes down to the economics of the application. So what makes best sense, CapEx and OpEx? What we find is that when you get into operations, if I was to summarize the market space that we play in, is that where RO kind of stops at around 35,000 ppm, that's where we take over. That's an optimum range for us to begin at. And we can operate all the way up to 240,000 ppm. In that range, you take a look at other conventional technologies such as evaporators, which are bulk boiling, a lot of energy to boil off water. Is that when we do a comparison, is that our sweet spot or maximum area of advantage is that if you had an evaporator, we could replace an evaporator and deliver the same performance and the requirements that this thermal evaporator could do, as well as be able to go and operate in a range that an RO would not. So this is where we lie within the market space, is beyond the operational range of reverse osmosis, but also in the range of an evaporator. As I said, we can produce without thermal bulk boiling 240,000 ppm, pretty much the same as a thermal evaporator without the energy consumption. So bringing it all together to take a look at, well, what does the FO system look like? Well, you start off, this is the FO membrane. Waste stream is on one side, and we have, remember we talked about the solute, the draw solution on the other side. And as the waste stream comes by, we pump our a concentrated draw solution up against, on the other side of the active layer on the membrane. And that causes, from that osmosis, the osmotic difference is that the concentration on this side of the draw solution is significantly higher than this. So there's an osmotic difference or gradient, which causes the water to be drawn across. So our concentrated draw enters, we draw clean water across the membrane from the bulk solution or feed. And the result of that is that we now have a diluted draw solution. So we have a salt solution and water. And in most cases, well, I want the water, not the salt solution. So this is the uniqueness of FO, is our particular industrial FO system is the separation of the water from the salt. And how we do that is we take it into a stripping column and we apply low-grade heat from 60 to 90 degrees. And that low-grade heat has enough energy to cause the salt, the draw solution, to go into a phase change. So it causes it to go from a liquid to a gas. So it phase changes to a gas and it leaves solution. And of course, when it leaves, what it's leaving behind is pure water. We then take, as it phases to a gas, we then collect that gas, cool it, and then reconcentrate it back into a draw solution, and then recirculate it back into the system. So the FO system is completely, it's a draw, it is a closed loop solution, a closed loop process. So we draw water in, it dilutes, we draw water off, collect the gas, and then recirculate it through. The draw solution that we use is, we'll touch on it next, is TMA. It's not an organic, so it doesn't break down. So it's going to last for the life cycle or design life of the system. So what is, I'm going to say, our secret sauce? It is a trimethylamine draw solution. What we do is we then react it with CO2, and it produces a trimethyl ammonium bicarbonate. That is the uniqueness of the solution. What that is, it is unique and it's patented and well differentiated. It creates what we call a switchable water salt. And as he said, when you take in that the draw solution, the salt, and you hit it with a low grade heat, again, what happens? The TMA phases to a gas, the CO2 phases to a gas, and the CO2 is left behind. And the result of that is that you have very, very pure permeate. Typically, I'll give you an example. Instead of it was 200,000 ppm coming in, I would expect anywhere from 150, maybe 200 ppm within my permeate. So a significant difference between 200,000 to 200, rule of thumb. It is a closed loop system, so once the system's charged, it's going to continue to reprocess and reprocess. And the last aspect of it is that the legacy of FO, people used ammonia, and ammonia had a tendency to creep across the membrane. So not only are you pulling water towards the into the system, what would occur is that you're also putting some draw back into the solution. So with our process, in association with we use aquaporin membranes in our draw solution, it basically locks everything in. So that's our closed loop, and we've eliminated reverse salt flux. So something that's very unique, and I can talk about that at a later time. The other component, as we said, uses a low grade heat. It allows us to tap into unconventional or other heat sources, as we like to call it, a flex heat. So it could be, if it's down south or maybe Saudi Arabia or UAE, we take a look at solar thermal. We can use the heat coming off from the geothermal. We can also take a look at boiler blowdown. There's several aspects, because we're looking not a large quantity of energy, so we can tap into these different flex sources. So the aspect of that is that, well, if we tap into those waste heat, then my OPEX cost significantly goes down. It also plays into ES&G because I'm not producing the CO2. So what does the system look like? So the industrial Forward Osmosis system, if you can take a see here, is that this is the fluid, this is the TMA, this is the CO2, that's the draw solution. This is the membrane modules. Again, depending on the flow rate, we can add additional modules or take them away. One of the keys to DLE is, with DLE projects, they're typically in stages. And the approach that we've made is modular, is that as the production demands increase on the DLE, we can also add additional modules or expand our system out in conjunction to that. So we can stage as the DLE process stages. And the last is the column. So as I said, is that we need to heat up that solution in order to induce that phase change of the salt. So we have a stripping column where we apply heat. And then to capture the draw and bring it back, we have an absorption column where we cool it and bring the gases back into the solution and reconcentrate that draw. That's the process. So What are the different configurations? Is that DLE processes, there's a lot of variabilities and so on. So when we approach it, we have within FO, we have a lot of flexibility within our design. And the driver that the driver that we have in the focus, of course, is the economics. What makes best sense? And part of that, when we do an audit of the plant or the application, is looking at, what do we have access to? Do we have access to waste heat? And another one here is, do we have access to a sacrificial draw? What do I mean by that? Well, remember, FO operates as that one side, I have a salt solution or a solution that has high solute. Well, that could equal seawater. Seawater is about 35,000 ppm. If my feed stream or concentrate coming in, whatever that is, it could be a process stream, I can use the salt water to actually pre-concentrate or really remove all the water that I need. So it is something to have access to. Or in DLE processes, sometimes what we can do is the actual brine itself, we can use the depleted brine to act as the draw solution in which to drive a lot of the processes of the concentration within the DLE flow sheet without the use of any energy. So it is a spontaneous reaction, osmosis, and if we can do it with a sacrificial draw, it means that our OPEX and our CAPEX cost is significantly low. So we are constantly looking for opportunities in which to use sacrificial draws. The other component to it is sometimes is that, well, we need to concentrate it a bit more, and we do have access to a sacrificial draw. So what we will do is we'll use the sacrificial draw to pre-concentrate, extract the water, and then we will feed the concentrate to the FO process with regeneration, and that will take it to the next step and concentrate it up to 240, 260,000 ppm. This process is very effective by having the two-stage approach. Again, it allows us to reduce our energy costs and also our CAPEX costs as well. These are great, particularly when there's ESG concerns, and we're trying to, get our process to be green lithium or get our the process requires like a net zero. So this is very beneficial to those requirements within those DLEs. Other configurations is just a standalone. There is no access to a sacrificial draw, so we just operate the FO system by itself. This is what very easy process, standalone, 95% recovery, 95% from water, and it has a very wide and robust operating range. As I indicated before, is that we want to take a look at, we want to tune the feed in order to optimize the DLE. And with FO, we have a very wide operating range from anywhere from 35,000 ppm all the way to 240,000 ppm. So we can take swings within the feeds, not the dynamic responses or something, but we can accommodate changes within that feed streams. And the last configuration, just to talk about, is what we call a ROFO or an ROFO, which is I'm going to say 50% within the DLE flow sheets that we take a look at. And part of that is that some of the streams, I'm going to say on the process side, not on the DLE process, but from your boiler water, your cooling water, maybe the LU coming from some of the processes, is that it's low TDS. Let's say 10,000 ppm. For us to put an FO system in, I wouldn't advise that. To me, the economics are there because the first thing I'd say is that, well, an RO can accommodate that quite nicely. But if a plant is looking to really get the recovery up to like 95%, then this becomes really an opportunistic approach, is that I can now, rather than trying to stress the RO to get very high recovery, let's say 65, 75%, is that, well, now what I can do is I can take some of the loading onto the FO. So I can optimize the system by, look, I'm going to run my my RO around 50% recovery. it doesn't really matter because I'm going to feed the concentrate over to the FO and it's going to do the bulk of the work. So a lot of these applications will take a low, could be even 5,000 ppm. This configuration allows us, I'm going to say regardless of what the TDS is, to concentrate it, to extremely high levels and reduce volumes down, 95% recovery. So this is probably has the widest operating range and probably the most robust. Again, we do take a look at the economics, and that's why we have those other configurations. So now taking a look at the applications.
So there's a lot of material.
One is just on the brine ponds. These are salars down in South America, so I won't belabor this. But one of the things we can do is that, well, the biggest challenge that a salar has, even though you're doing solar evaporation, you're not putting energy into it, so it's relatively green. Well, if there's a rain event, well, all that water goes into the ponds. And if you're relying on thermal evaporation, that could delay your lead time for delivery significantly. It could be 6 months out, could be longer than that, depending on how much rain. So what we've devised is that, very simply, is that we would have a takeoff weir or boom. We would draw on that water, so it's essentially rainwater with some salt into it, and we're going to concentrate that up through an FO system. And then the concentrate is then returned back to the solar pods. So what that allows us to do is that you have this integration into an existing operation, but allows us is that we're, that variability, if it rains, well, okay, now you got to push out your lead times, and who knows, maybe the client needs it. So it allows us to improve and really take away the variability in a variable on the lead time. So you remove, even if there's a rain event, it doesn't matter because we can operate the system. So how that system would be set up is that these are these aquaporin membranes as a module, is that we would do, because the size and the, I'm going to say the location of these, they're displaced, it's decentralized. We would have multiple RO modules set up, and we'd have a centralized regeneration plant.
Could the crosstalker
drawing
turn
the water
off
off
the mic,
these,
please?
it goes back, it gets concentrated, and the concentrate goes back. And the other component to this is that the byproduct of the process is pure clean water. And in South America, that's a real concern.
Chuck B,
So other
please turn
processes,
off your
this
mic.
is very much of a generic. It's taking the brine in. Again, this could be ion exchange or absorption. I remove the lithium from it, means that the brine is now depleted of lithium. The brine is then passed into another reactor. It could be washed. But typically at this point is that I want to make sure before I move it into my next phase, I want to make sure that my calcium magnesium removed. So I'll precipitate that out through different chemistries. It's a conventional chemistry approach, physical approach, so nothing complicated. This is kind of the magic. This is kind of not that magical. And then we'll take that once the hardness and some contaminants have been removed. It'll flow into the FO system, where we'll then concentrate that up, and then it will pass into, I'm going to say, the last phase, into the polishing. Very generic. There's other components to it, just to give you an overview. Another application to this is this is through Aramet, and again, let me just put a note here. I've just taken their process and said this is kind of how I would have approached it. You can see here they have their absorption column. It's going through, I believe, an MF or nanofiltration, RO, thermal evaporator, and then off to conventional chemistry. The way I approach this is that, we could eliminate this, and this by having simply an FO. So you've got 3 unit processes I can eliminate. So my CapEx and OpEx drops significantly down, but I'm still delivering the same performance and the requirements of the system. So give you a little bit of flavor of what FO is capable of. So, and just closing this up is, if there are interests of working with us, the first step we do, like anything, is to qualify, is we do computer modeling. So you give us an analysis, or at least tell us what the characterization is, and then we're going to computer model this to make sure it is a go. If it does pass, then what we do is we ask for samples because there's nothing better to eliminate variables or unknowns than to have a physical sample. That's passed off to our engineering facility and lab facility in Sarnia, where a sample is then physically passed through FO modules, and allows us to quantify and qualify some of the operating parameters. If that's work and still feasible for the client, it then goes into our in-house pilot plant testing. So we've spent a considerable amount of money and time building this complete industrial FO system.
And we
It
do try to
processes
sprinkle them
about
in
a
because
cubic meter a day, but it's the
you're saying, I
complete
missed this section,
FO
by the
system
way.
scale.
I did that with
So
the
it allows
design,
us
but
to
it's
take
better to the section and
client
highlight.
samples, barrels, and pass that through the system
I appreciate
and get a whole bunch of empirical data, which really allows us to validate and eliminate any issues, but more so allows us to optimize the performance of the system. And then lastly, if that's a go, a green light, and the client wants, we have a mobile system, which is 35 cubic meter, typically, I say mobile, slab on grade or gravel, which we deliver to site and hook in. And now we have a live feed. So even though this is about, I'm going to say 85, 90% validated in the design, as we know, sometimes at 3 in the morning, someone might kick a valve and so on. So it's good to have a live stream because it allows you to identify variables, instances that you wouldn't have picked up in static samples. And that is the end of our presentation. Again, I can come back and say, I'm so sorry and I apologize for technical delays and for you still online. Thank you for holding on. And at this point, I'll take any questions that you have.
Sure. We'll share that practice with you, and that's an individual basis. So you can say, hey,
just so you know, the way that we go to market is we typically have manufacturer representatives located in different parts of the world. So that allows us to have local boots on the ground. So if you are interested, I mean, call me directly, or I can get you in touch with our local manufacturer.
We'll try to get that best practice working for people, and we'll let you know how that will work in the future.
So it doesn't look like we have any questions.
Super. Well, thanks again, Yusuf. Appreciate it. We'll talk
that. Everyone, I really appreciate your time. Feel free to give me a shout.
Hey, Joseph, how are you?
And hey, have yourself a great day. And hey, I look forward
I literally
to
just talking off the session. So
thank you very much, everyone.
I said bye
Appreciate
and
your time.
picked up the phone.